So this is a fan controller PCB I designed as a personal project. It's a relatively small board, about 60 by 40 millimeters, roughly 2 1/3 by 1.5 inches, and it's intentionally kept compact while still being easy to reason about. What I want to do here is walk through the layout, the interfaces, and some of the design decisions behind it. This isn't meant to be a tutorial or a deep dive into every detail. It's more of a design walkthrough explaining how the board is structured and how it came together. The board is being used here to control a fan based on temperature. There's a microcontroller for the logic, a power stage driving a fan, a temperature sensor, and support for external user interfaces and feedback. The underlying hardware itself is fairly general purpose. It includes USB for both power and data, automatic power source switching, and multiple external interfaces. And the way the board behaves is largely defined by the firmware rather than being locked to a single function. One of the main constraints here was the size. At about 60 by 40 millimeters, there isn't much room to spread things out, so placement ends up doing most of the work. The microcontroller is on the far left side of the board. Directly underneath the MCU is the JTAG connector, which is used for programming and debugging during bring-up. Immediately to the right of the MCU are two status LEDs, one red and one green, in 402 packages, used for basic visual feedback. To the right of the LEDs is the SPI connector for the rotary encoder. That interface connects to a separate rotary encoder PCB that I designed. Near the top left, there's also a serial UART connector sitting close to the temperature sensor. That's mainly there for debugging and bring-up. Directly above the microcontroller is the I2C connector, which supports an external display. Near the top center of the board, there is a single-pole, single-throw switch, which provides simple local user input. On the right side of the board, the fan connector and the battery input connector are placed close together on opposite sides of the PCB near the power handling circuitry. USB enters the board through a single USB Type-C connector along the bottom edge. That overall structure makes it easier to understand how signals and power move through the board without having to trace individual nets. I used a 4-layer stack-up for this design. Signals are on the outer layer, there's a solid ground plane on layer 2, and power on layer 3. On a board this size, that helps in a couple of ways. It makes routing easier by providing a consistent reference plane everywhere, and it also helps minimize ground loops and unintended return paths. I wasn't trying to minimize layer count or aggressively optimize for cost here. The goal was predictable behavior and a layout that's easy to reason about. Not to mention 4-layer PCBs are relatively cheap these days. The board operates from a 5-volt rail, which can come either from USB Type-C or from the battery input. There's a linear regulator on the board that steps the 5-volt rail down to 3.3 volts for the microcontroller and other logic level circuitry. A linear regulator made sense here given the current levels and helped keep the power design simple and quiet. To make bring-up and debugging easier, I added test points for all the main rails. There are dedicated test points for the 5-volt, 5 volts from USB, the 3.3 volt rail, battery voltage, and ground. Having those test points available makes it much easier to verify power behavior during initial bring-up and to diagnose issues later without having to probe fine pitch pins. Starting again on the left side of the board, the serial UART connector near the top left is mainly intended for debugging and bring-up, and it sits close to the temperature sensor for convenience. Immediately to the right of the microcontroller are the red and green status LEDs, which provide basic visual feedback during operation and bring-up. Just to the right of the LEDs is the SPI connector used for the rotary encoder board. Above the MCU, the I2C connector provides the interface for an external display for things like temperature or fan speed feedback. The single-pole switch near the top center provides simple local control. The fan connector and the battery input connector are kept close to the power control circuitry. Placing those near each other helps keep high current paths short and localized. USB is brought in through a single USB Type-C connector on the bottom edge of the board. Grouping the interfaces this way helps avoid crossing domains unnecessarily and kept routing relatively straightforward. That flexibility is intentional. The board can support different use cases depending on how it's configured in firmware. One of the more interesting parts of this board is the power strategy. The board can be powered either from USB Type-C or from a wired battery input, and it switches between those sources automatically in hardware. From the rest of the system's perspective, that switchover is transparent. The USB Type-C interface supports both power and USB 2 full-speed data. The data path is present so the board can support networking or other USB-based communication later on, even though the current firmware doesn't make use of any of that yet. That was a scope decision rather than a hardware limitation. USB is treated as a fixed 5-volt source on this revision. There's no USB power delivery negotiation because the board doesn't need variable voltage or any higher power requirements. Keeping that behavior simple made the overall power system easier to reason about and easier to bring up. The power control and source switching circuitry lives on the right side of the board, close to the fan and battery connectors, which keeps current paths clear and easy to follow. One thing that's worth mentioning is assembly, especially for some of the smaller components. The USB Type-C connector isn't something you can realistically solder with a standard iron. You really need a heat source like a hot air station or a heat gun to get proper reflow on that footprint. On a board this size, it doesn't take much airflow to move parts around, so that's something to be mindful of during assembly. I also added a QR code and my logo to the silkscreen. The QR code links back to the main page of my Build and Charge website, buildandcharge.com, which makes it easy to tie a physical board back to documentation or project context later on. It's a small detail, but it's been useful in personal projects. I think it looks cool. At this point, the board is built and working as intended. It's small, predictable, and easy to understand, while still leaving room for the hardware to be reused or repurposed for other applications depending on the firmware. If I revisit it in the future, it'll likely be to refine details or apply the same approach to something more constrained. And here's a 3D rendering of the design, showing all the components placed with silkscreen in all layers. So just for a final overview, we have the temperature sensor, the UART TXRX, the I2C display connector, the SPI rotary encoder connector, single pole, single throw switch, the fan connector. Here's the power control circuitry, including the power switch, USB connector, JTAG for programming and debug, and the MCU. And on the rear, we have the power connector. And finally, here's a demo of the fan controller in action. At the top, you'll see the PWM control to the fan, controlled by a user switch. Thanks for watching.